we're going to translate telephone numbers written as digits and letters into their corresponding plain numbers. So first, here is the telephone keypad. If you look at the letters, they are sequential and they kind of split the alphabet into into groups, kind of sub-alphabets. And since that's the case, then we can see the alphabet as a range and have some cutoff points. And then we can just say between which cutoff points does any particular letter occur. So the cutoff points would be the first letter from each key. So this is the first function and the each operator, and then our keypad. We don't actually need this to be a matrix anymore, so we're just going to, well, I can actually just flatten that, ravel it. And then we have some spaces in the beginning and the end. We can do the intersection of the alphabet and these. And that gives us just the letters that we wanted. And we can give this a name if you want. So these are the cutoffs. Okay, so now we have the letters of the alphabet, and we can use the interval index into these letters that we have stored in C. And these are the correct numbers for the individual keys, but offset by 1. We can fix that either by adding 1, or we could add a placeholder character that doesn't actually appear on the left. So we need to use something that keeps the increasing, or at least non-decreasing, series of letters. We can use the character that in Unicode comes right before A, which is the @ symbol. Okay, so now we have the correct values for the letters of the alphabet. What about the digits? Well, the digits we have here in quad D as a constant. We can look these up in itself. And even though each interval here is just a single one, that works fine. But we're off by 1. Again, we need to subtract 1. And there are various ways we could do that. One thing that's interesting to observe is a character that appears before the first cutoff gets an interval index of 0. So if we drop 1 from the alphabet, this dropped the 0, then when we do the interval index, we get the correct values. Okay, now we can put all of this together. If we take the digits, but dropped 1, and we concatenate, it doesn't matter when we concatenate, if we concatenate first or drop 1 first, because it's such a short amount of data here. Then we have a full vocabulary of cutoff points. Anything from here is 9, then this becomes 10, this becomes 1. Oh, but it needs to be 2. So let's insert yet another @ symbol or some other symbol that appears between 9 and @ or A. And now we can try looking up all the values. And so these are the digits. and these are the letters. But now they are too large by 10. We can fix this since everything needs to be mapped between 0 and 10 by taking the remainder when dividing by 10, or the residue, we could also call it. So that just takes all the 10s away. This is also known as modulus, but we take the number we divide by on the left. So this fixes the issue for letters, and digits stay just the same. And that's really all there is to it. In order to make this into a proper function, then we want to apply this dyadic function with a constant left argument, so we can bind that left argument to the interval index function, and then we just assign that to f. And now we can see that telephone numbers get mapped correctly, and digits as well get mapped correctly. So we get the values that we asked for. This isn't the fastest thing to do, because if we think about it, this is a simple mapping. There is a mapping where we look up a particular value and then we give some other value. And we can define a function that does this as a simple mapping. So let's first generate all the values that it could be. These are digits and these are the characters. So this gives us all the values for all the digits and letters that could appear. We can call that n for now. Then we can look up the input in the list of all digits and letters. Like this. And we can define this as a little lambda or defen. So this just gives us the indices. It doesn't matter what exactly they are, because we take that result, all the indices that correspond to the input letters, characters, numbers, and we look those up in n. And then we can try that as well. And see we get the same result. And this is of course going to be the fastest solution because we're not computing anything, we're just looking up. If we want a self-contained solution here, then we could take all this, do 2 parts, and put in the literal number here, and we want 999 at the end. It's a bit long, but it works the same. Thank you for watching.